Let's consider how to integrate the analytic function over a closed contour in the complex domain. Here shows the concept. The domain of the, you know that this is G domain. G value is consisted x plus jy. Okay, this is x plus gy. Jy. Okay, this one is a domain. This C contour means a path, closed path. It's a closed path. Starting from here, turn back to original point. Then this closed contour creates some area inside of this contour. Is referenced as S. So this one is the area of inside of the closed contour. So we would like to take integration on the contour. At every contour point, we would like to integrate function fg. That is shown here. So closed contour expressed by this nibbles in the middle of the integration symbol. So C means this contour taking closed path. Fg is function fg. We would like to evaluate every point on the contour. So each G point, G means this contour point. We would like to integrate that one. So to integrate that one, Fg is expressed the U plus J omega. U is the real part of the Fg and the imaginary part is Vg. Okay, this one. And the dg, you know that G is this one, so dg consider dx plus J dy. So this is dg. And by producting between these two complex functions will give along this contour we need to measure this one. And the J imaginary part is this one. So we need to take a contour integration of this value. It shows a little complex. By use of the Green theorem, we can change the contour integration to the area integration. Okay, this is contour integration, but we would like to change that one into area integrations inside of here. Then we can make it simple. Here shows the result of the Green theory. Green theory says that the contour integration of the real part of the complex function over the dx integration should be equals to the area integration for the differentiation of the u to the y and dx dy, and the similar the imaginary part of v times dy equals to this one. Before to prove this one, I would like to mention that the contour integration always has some directions. The area is positive directions, means that the positive area means this one. If contour integration taken the counterclockwise directions, then this area is a positive directions. Okay, so this one is seems like a right-handed rules. If we turning the right-handed this one, right-handed thumb direction corresponding to the area direction. So contour and its corresponding area is a positive direction, by use of the right-handed rules. The cross product rule, or it says that the direction of the area and the direction of the contour. So integration direction is important to follow the correct path. It means that the positive direction is always counterclockwise. If the integration direction is opposite, the sign is changed. So keep in mind this part. Now we would like to prove this part. Then we will back to this point again. Okay, here is the real part integration of this one. Okay, among these two integrations, we would like to consider this part first. Okay, that's this part. So here is the integration domain. The contour shows this one. At this moment, x and jy are given here. The starting of the x is x0 and ended at the x1. And the y starting from y0 to the y1. We would like to integrate over this contour. Then contour consists of 4 segments. Segment C1 and C2 and C3 and C4 consisting the closed contour of C. Okay, so we would like to integrate closed contour function. Okay, then it gives this real part integration and imaginary part integration are given. That's the same as this part. So how are we gonna changing contour line integral into area integral. Okay. So from here, what's the meaning of these integrations? Okay. This integration means u should be u is a function of x and y. This value should be integrated on this contour C1 and C2 and C3 and C4. So this integration means a sum of 4 segments, I changing from 1 through 1, 2, 3, 4. That's this is sum of I. So we have to take integration C1 plus C1 dx u and the C2 u dx plus C4 C3. Okay, sorry. I would like to rewrite this part. So integration over C1, that's this segment, and u dx. And the next segment is C2 segment u dx plus C3 segment u dx. Lastly, the C4 integration u dx. This one is this one, and that should be equals to whole closed contour integrations. From here, the second contour and the fourth contour, x doesn't change. So you know that x changing from the same point x1 to x1. Okay, x1 integration from this point to this point, x changing from x1 to x doesn't change. It's the same. This one is x0, x0. So okay, C2 is this one, x0, x0. Sorry, this one is x1, x1. x1 and x1 is this part. The x0 and x0 is this part. So segment C2 and C4 is vanished. It doesn't change x. So we have only 2 segments are remained, non-zero value. So we would like to consider that one. That one of them is shown here. The first segment x changing from x1 to x0 to the x1. We have to take integration from the x0 to the x1 to follow the positive direction. Positive direction is a counterclockwise. We have to take integration like this direction, counterclockwise directions. So dx changing from x0 to the x1 and u x, and at this moment y is 0. At this segment, on this segment, y always y0. So we can take integration in this way. And what about the segment 3? Segment 3, x changing from x1 to the x0. So opposite direction for C1. So x changing from x1 to the x0. So dx, x changing x1 to the x0. And at this moment, u, x, and y1. So in the segment 3, y value always remains in the y1. So it's a fixed value, these two things. And then we can make it the one integration by use of x0 to the x1 integration, that this one remained in the same way, but this part should be changed the sign in this way. So this is the u dx of the contour integration of contour integral for u dx. So we would like to see this one a little further. Look at here. So this part can be rewrite here, x0 to the x1, and change the order. Okay, y1 comes first, so minus sign is come out here, and divided y1 minus y0. So this one gives delta y. Okay, this one is delta y. Okay, and multiply the same delta y. So it should be the same. Okay, but the same result can be written like this way. So dy changing from this variable and take the derivative like this way. So carefully compare. This one is the same. This one definition is differentiations. This one is integration over the y0 to the y1. So we can write this part as a du of dy And to compensate this one, we write down here dy and the integration from y0 to the y1. So by taking the integration with respect to this one, the dy will cancel out and this y1 minus y0 will be multiplied, and we have the same this result. Okay, so that's why this part becomes in these double integrations. So double integration means area integration. You know that two different lengths is producted, that's the area, and this one corresponding to the inside of this area of S. So delta x1 minus x0, that's the this part, this length, and y1 minus y0, this length. So integration range now becomes the S. I mean that these double integrations, x changing from x0 to the x1, y changing y0 to the y1, then this area factor cover the whole section of S. S is this area closed by the contour C. So you need to understand the relationship between closed contour to the area S. S is the closed area by the contour C, closed contour C. So we proved the first Green's theory. This integration should be equals to this one. That is this result. Okay. The second one, we would like to take a contour integration of v dy. That's the another real part of the complex integration. Okay, this part. So this part are integrated over the same contour. Similar techniques, we can integrate the all segment of the contour C1, C2, C3, C4. At this moment, we have to integrate over the y change, but the C1 and C3, y doesn't change, y remain y0, y1, like that. So we have to take integration over C2 and C4. So firstly, we would like to integrate from this part is a C2. So this one come from C2. We would like to integrate them from here to here. So y changing from y1 to the y1, y0 to the y1, y0 to the y1, y0 to the y1. But at this moment, x remained constant x1. So that's this one. And take the integration along the y. And C4 changing from y1 to y0. So integration direction is y1 to y0. And at this moment, x remain as a constant x0. So this should be x0. We take the integration along the y. So similarly, we can find out this result. So that result can be rewrite the same reason why we can write that one double integration or area integration by changing this one. So this is another result of the Green's theory. That's this part. Then by use of the Green's theory, we can rewrite this difference. Okay, you know what? From here, these two S are the same. So both of those S are the same things. We have the integration this area when we take the double integrations. So the result is this one. So the real part of the complex integration, okay, real part of the complex integration is this part or this part equals to, you know that this part this contour integration gives these double integrations, okay, and v dy contour integration are given this way, but there is a minus signs. Here is another minus signs. So we factor that one out of the integration like that. Then we can sum up these two differentiation factor and the area factor. But we know that the Cauchy-Riemann conditions, this should be 0. Could you see here that that is the Cauchy-Riemann requirement? Okay, this part should be 0. Okay, that's why real part of the closed contour should be 0. Okay. Similarly, we can apply the same technique to imaginary part of the integrations. So closed contour integration, this contour is this one, and v dx and u dy becomes the imaginary part of these closed integrations. Here shows the result. So the closed contour integration v dx, x changing over this contour, and it will give these double integrations, area integration are given this way. And for the another imaginary part is u dy. Taking the contour integration, you can follow the same rules, then you can prove it. It's an area integration given like that. To find out the imaginary part of this, we need to add up these two terms. By adding these two terms, it becomes this one. But look at this one. This one is another Cauchy-Riemann conditions. That's the this Cauchy-Riemann conditions. This one. So partial u of partial x minus partial v of partial y should be 0 to satisfy the analytic conditions. Okay. So this one should be 0 because of these Cauchy-Riemann conditions. Then we can understand that for any given analytic function integrated over a closed contour should be 0. That's the result of the Cauchy-Riemann conditions. Before close out this one, I would like to mention the contour shapes. At this moment, I just assume that the rectangular contour shape, but we can expand any kind of contour. Here shows the stories. We have many small contours, the CI, CJ, CK, whatever. If there is any given contour C, then we can make an infinitesimal small rectangular contour created over here. Then what is the closed contour integration of the complex function? At this moment, the closed contour is any shapes of this one. This one is a closed one. By this closed contour, the area are created inside of this contour. Okay, so this contour integration can be expressed by the sum of its small segment. Each segment has integration all these directions, but you know what? Inside the integration, one is a positive direction, another one is a opposite direction. So the integration of the inside will cancel out each other. Only the almost path, only this path terms are remain. All the inside terms are cancelled out because of the integration directions. So by summing up small segment as we have done in here, that is one small segment. So by summing of each segment will give this one, but each segment can be expressed the same as the area integrations. So each area integration is a sum up, then that is the whole area will covered. So this one is the double integrations, but both of them should be 0 due to the Cauchy-Riemann conditions. So it doesn't matter the shapes of contour shapes. In any kind of contour shapes, closed contour analytic function integration should always be 0 due to the Cauchy-Riemann conditions. Okay, here is an example. Show the following closed contour integration of fg equals g square should be vanished. Okay, fg are given this way. At this moment, u and v are given in this way in case of fg equals g square. By taking contour integration, u to the dx will give this result. Okay, by taking integration, the contour c1, 0 to the x1, x0 to the x1, and x square minus y0. At this moment, this is y0 over the path of c1, and the c2 path is 0, the integration, because x doesn't change, dx is 0. So what about the c3? c3 changing x1 to the x0, x1 to the x0, and x square. At this moment, y remain at the y1 state. So y1 are given here. By taking integration, you will find out this result. But by use of the green theory, we can change these integration into double integrations, area integration. At this moment, the area is the S, area covered by x1, x0, x1, y0, and y1. So double integration will be covered the x0 to the x1, this area, and y0 to the y1. Okay, that's this integrations. And the partial u over partial y, by taking derivative u with respect to y, it will give minus 2y. So minus 2y is this one. By taking integration, x doesn't show up, so x integration are given the difference of x1 and x0. That's this one. And taking integration with respect to y will give minus y square. Okay, but this minus will cancel out this one. Then this should be y2, y1. y1 square minus y0 is this part. So you can see these two parts are the same. So line integral, this one is a line integral. Line integral result equals to double integral result. Okay, that is the green theory. We talk about the green theory over here. That's the shown here. So green theory is quite useful to taking complex integrations. So another contour integral for the real part are this one. You can do the same way. At this moment, we take the line integral first. The line integral is performed C2 line changing y0 to the y1, y0 to the y1, and x remained as x1. So Vx remained x1. So this is the V value at this contour, and y changing from this region, and the C4 section, y1 to the y0 change, y1 to the y0 change, and the x remained x0. So this is that one. By taking integration with respect to y, it will give this result. And by use of green theory, we can change the line integral into the double integrations. By taking derivative v with respect to x, it gives 2y. So 2y should be integrated over the area. So by taking the integration, it will give this result. So you can prove that this is the same. But the real part of this one should be difference of between the two. We have to subtract these two things. Then this one is 0. That's the result we have proved previously. So we proved the real part of this integration is 0. You can do the same technique to prove that the imaginary part also will be 0 because this is analytic function. So analytic function integration over a closed contour always 0 due to the Cauchy-Riemann conditions.